Hi, everybody. For today's lesson, we're going to be talking about a super important concept in physics, vector components. This is going to be one of the most important tools in our physics toolbox. It's going to be used in practically all of the content we cover for the entire year. With some practice, you'll get really good at it, and our goal is to get really good at it because we're going to want to use it often and quickly and effectively. So please make learning this lesson really well a high priority. Okay, first let's go over to a little simulation so we can kind of conceptualize what we're talking about when we talk about vector components. Okay, so here we can see that we've got a nice little setup for showing vectors, right? We've seen this one before. I can grab a vector and put it on here, and I'll start it at the origin because that's kind of nice. I'm going to turn off my values, and so I've just got a single normal-looking vector, and I can make it any size I want. I can move it around. I can grab it, and I can move it like this as well. One of the important lessons we learned, and I'm just going to put this in a nice spot where it's kind of like easy to see what's going on. One of the important lessons we learned earlier is that you can, when you add vectors, as long as they start in the same place and end in the same place, they are equal to one another. So I've got this vector that's labeled as v. I could take a couple of orange vectors and I can start them in the same spot. And I could have this vector go like down here, and then I can add another one that's going to go over here, and then I can add another one that's going to go like down over here, and then I can add another one that's going to go over here like this. And as long as they start and end in the same place, they are equal to one another in terms of vector addition. So the single blue vector is equal to these four orange vectors. They start and end in the same place, so we say that in terms of vectors, they are equal to one another. A way to think about this that makes sense is in terms of like forces. A single force like the blue one going that direction and that magnitude would equal these four orange forces, if applied to the same object, they would work out to be the same thing and they would move the thing the same amount. So that's how you can think about it, that although you think like these shouldn't be equal to one another, they actually are. If you apply the four orange forces or the single blue force to an object, they would work out the same because the orange forces go in different directions and kind of like counteract one another. Okay, let's clean that off here. So we say, okay, we understand that's true. If vectors start and end in the same place, we say they're equal to one another. So this gives us a nice little trick that we can do. We can have a vector start here and end, I don't know, like maybe over here. That means if my vector starts there and ends there, I can actually take two vectors. I'll put an orange one that's going to start here and end here, and then I'll take another one that starts here and ends here. Those two vectors are equivalent. The two orange ones are equivalent to the blue one. And this is like actually really useful because when we look at this, the blue one is at like a weird angle, right? It's not horizontal or vertical, it's at its own weird angle. So if we can take the blue one and instead express it as two vectors that are at really nice angles, one that goes horizontal, one that goes vertical, or if we're saying north, south, east, west, we might say the first orange one is going east and the second orange one is going north. It's really nice when we have vectors that are conforming really nicely to our geometry like that. They're easier to work with, right? So we might say, okay, for this blue one, we can, instead of expressing it as the blue one, we can express it as the sum of the two orange ones. Nice. Now, there's actually in this program a way to do that without me having to put out the orange ones. I'm just going to click the button here and it's going to show the vector components, which is nice. Now we can actually add values to this, right? So I see that one vector component has a magnitude of 20 and it's going directly, in this case, we look at the x and the y axis. So we would say it's in the positive x direction. And then we have another one that's magnitude 15 that we would say is going in the positive y direction. And it's really common to express these vector components as x's and y's, right? We label them as x's and y's, and we say there's an x component and a y component. And any vector is going to have an x and a y component. Now, of course, you could have a vector that goes straight up and down, in which case it has a y component, but the x component is 0 in this particular case. It doesn't move in the x direction at all. And as I move this, you can see how the components change, right? And I can also have negative components too. Let's move this up a little bit so you can see it a bit better. If I go downwards, now I've got a negative y component and a positive x component. My x component is 22, my y component is negative 9. I can also express this over here. Now I've got two negative components. My x component is negative 17, my y component is negative 11. Now, so we say, okay, we can take this one vector and break it into two parts, and those parts go at nicer angles for us. Cool. And we'll express one vector instead as the sum of two different pieces. Here's a cool thing though. We can actually, if we put this vector away, let's turn off our components for a second. We can talk about the sum of vectors. So let's say I have a vector that starts here and goes to here, and I have another one that picks up right where that one left off and goes over to here. And then I've got a third one that goes from here and then goes all the way down to here, right? I would say, okay, what's the sum of these three vectors? Well, I could draw it with the orange one. I could put it here and do it like that. That we would say that is the sum of those three vectors. We add them together and we end up in that spot, and we can go directly there with the orange one. Those would be equivalent. We could also get there by adding up the components. So let's put our components on here. I want to note that for my first vector, I've got an x component of 10. For my second vector, I've got an x component of 15. And for my third vector, I've got an x component of 10. I add those up. That's 10 plus 15 is 25, plus another 10. We make 35. So I have an x component of 35. My y components, I have a positive y of 10. I have a positive y of 5, and then I have a negative y of 10. I add those up, positive 10, positive 5, negative 10. I get positive 5, right? So I can add up all of my x components and all of my y components, and that's what we'll usually do. Now, if I put on my orange vector and I draw it like this, you'll see that the components of my orange vector are equivalent. My x components are positive 35, my y components are positive 5. So by taking all the x components of the three vectors and adding them up, and all the y components of the three vectors and adding them up, and taking into account that some might cancel out others because some might be going up and others might be going down. When I work them all out and add all of them together, I can, instead of drawing all of these weird blue vectors and having to figure them out with some weird shape, I can just draw this orange vector, and I have all of the x components add to 35 and all the y components add to positive 5. I'm going to show you how to do this in terms of a problem, but this is what we're doing when we want to simplify problems. The nice thing about using vector components instead of cosine law or sine law is this works for any number of vectors. Instead of only working for problems where I'm adding two vectors, which is very limiting, I can use this for problems that don't produce triangles. I could use this for 3 vectors, 5 vectors, 100 vectors, 1,000 vectors, adding them all up together. And if I want to figure out how far it goes in the x direction, I add up all the x components. If I want to figure out how far it goes in the y direction, I add up all the y components. So breaking our vectors down into x and y components is a super powerful way to add vectors together and figure out what's going on. It is, I think, the best tool in our toolbox that we're going to learn all year. Okay, so we've maybe talk that to death. Now let's actually try some some like examples and stuff and see if we can get a better look at what we're looking at. Okay, so we're back to our lesson note here that you've already seen, and let's just like chat about these quickly. So vectors have magnitude and direction. They could represent things like displacement, velocity, acceleration, force, momentum, impulse. Impulse is another momentum thing. We'll talk about that later. Electric and magnetic fields and more. They can represent all kinds of stuff we're going to study this year. So it's often convenient to express vectors as a sum of the horizontal and vertical components. Any vector can be split into its horizontal and vertical components. We often will just short form say they're x and y components. So we'll split vectors into their two pieces. And any vector can be split into two pieces. If it is a horizontal vector to start with, it would have no vertical component. If it's a vertical only vector, it would have no horizontal component. Otherwise, each vector will have both of those. We can use basic trigonometry to find the components. Good old SOHCAHTOA will show us how to do that. So it's going to be really useful. This is going to be easiest if we always use the angle adjacent to the x-axis. I'll show you what that means in a minute. We're going to describe for north, south, east, west, we'll call north and east the positive directions. And for south and west, we'll call those the negative directions. And this is going to kind of match what we think of when we talk about a Cartesian coordinate system, right? So we have our x's and our y's. There's our x's and our y's. These are our positive x's and negative x's, positive y's and negative y's. And if this was just a north, south, east, west, it would work out the same. It would basically be identical to that. So we could use either of those. Okay, so let's have a little look at our vector. The vector we see here is in purple. It's labeled v, which tells me it's a velocity vector. And I notice that I have my x and y coordinate system here. And I have a little theta here. That's the angle next to the x-axis. You're going to be able to standardize this and do it faster if you always use, let me get my highlighter here to just emphasize this. We always want to use the angle next to the x-axis. Okay, you can use the angle over here next to the y-axis, but it means you're going to have to switch your cosine and sine. And so it's easier if you always use the angle next to the x-axis. You can always be consistent with whether you use sine or cosine for our x and y components. So I can see in my picture, purple is my starting vector. That's my velocity vector. I'm going to break it into its x and y components. We'll usually label these in a very specific way, and you can see that's done here, right? Let me get my highlighter again here. You can see that Vx stands for the x component of the velocity vector, and Vy stands for the y component of the velocity vector, and we'll just use that subscript to describe these. Okay, so let's talk about how we get the x's and the y's. Now we know our cosine ratio is the adjacent divided by the hypotenuse, right? So if my angle is right here, my adjacent is this one right here. My opposite is that one right there. And my hypotenuse is the original vector, okay? So for cosine, it looks like I'm dealing with the adjacent side. That's my x component in this case. It's adjacent. And my hypotenuse. And for sine, I'm dealing with my opposite and my hypotenuse. So sine is always going to be associated with my y component, and cosine is always going to be associated with my x component. Now, I just want to mention, if you use the angle in here instead, the one next to the y-axis, you have to switch those, which is why I recommend always choosing your angle when you do these to be next to the x-axis, because then it'll be consistent. Cosine will always be x component, sine will always be y component. Okay, let's actually sub in our stuff here. So the adjacent side we call our x component, we label that Vx. The hypotenuse is the velocity, original velocity vector. For sine, our opposite side is the y component, and our hypotenuse is the original velocity vector. Let's just rearrange those a little bit, right? Let's multiply that v over, because we want to know the velocity, the components. We prefer to have those isolated. So there's our x component, there's our y component. So these are formulas that you probably want to write down and remember. They're pretty important, and we're going to use them all the time. To get an x component, we just take the vector and multiply it by the cosine of the angle between the vector and the x-axis. So the x component is v times cos theta. The y component is v times sine theta. That's always going to work as long as we're choosing the angle between the vector and the x-axis. Write those down, we'll lock them in your brain. We're going to use them all the time. Okay, let's actually try this out, hey? So we're going to determine the horizontal and vertical components of each vector. The first thing we want to do is draw the vector, just so we're sure that we're kind of doing the right thing. So let's get prepared to do that. Okay, so I've put my little grids on here just because that's gonna, make our life a little bit easier. So let's first draw our vectors. My first one I notice, and these should probably all have vector hats on them if we're going to be picky. I don't mind if you leave them off at this point because we want to, it's a little bit extra work we probably don't need to be doing. But we're going to try and draw our vectors. So our first one is a displacement vector. I noticed it says 30 kilometers north, 80 degrees east. So let's get our vector out and let's draw it. So I'm going to go north 80 degrees east. North would be straight up. I'm going to head towards the east. So I'm going to go like this. And I'm not going to go the whole way to the east. I'm just going to go most of the way there. Okay, there's my vector. So let's label some stuff in here. I know this angle is 80 degrees right here. And I should label my north, south, east, and west. And that means this angle in here, there's only 10 degrees left for this angle in here. And I'm going to try and squeeze that in. There we go, 10 degrees. Okay, so my angle next to my x-axis is 10 degrees. So I remember when I'm doing my components, that's helpful to know. So I'm going to write my displacement vector, but I'm going to put a little x next to it to show that I'm getting the x component. What does that actually look like if we were to draw it on here? Let's get an arrow and see what that looks like. My x component is going to look like this. My y component is going to look like this. Now I could label those if I wanted, right? I could say this is my delta dy, and this is my delta dx to show it's my displacement in my x and my displacement in my y. How big is that component though? Well, trigonometry is going to help us solve that, right? And we have kind of our shortcut that we worked out. I'm going to say it's the regular displacement vector, which is just right here. I can label that delta d as well, times cosine of theta. So my regular vector was 30. My cosine of the angle in between the vector and the x-axis is 10. There we go. Now this is going to be a little calculator work, right? 30 times cosine of 10. We say that's 29 point, a whole bunch. 29.54423. I say, okay, cool. I figured that one out. Let's round this off for significant digits, right? So we'll say, okay, this should round off to, looks like our angle 80 degrees has one significant digit, so that should round off to 30. Now I didn't write a direction here, but this is technically a vector. But here's the thing, since it is um, a component, and I know it's an x component, I know a positive x component is always going directly east or directly along that x-axis to the right. It's on the x-axis in the positive direction, or in this case, directly east. So I don't need to write directions in. I know exactly what they're going to be based on the fact that these are vector components. Let's do our y component. Delta dy is going to be the displacement times the sine of theta. So we had 30, and it's sine of 10 degrees. So we'll plug that in. We'll go 30 times sine of 10. That's going to be 5.2 and change. 5.20944. So let's round that off for significant digits, and that's going to round off to 5. Both of these would be kilometers, though. Kilometers and kilometers. Okay, and looking at them, that makes sense, right? The x component's big, the y component's small. Makes sense that it's 30 and 5. Okay, let's do our next one here. 25 meters per second, north 30 degrees west. Okay, so I'm going to grab another arrow here, and I'm going to say north would be straight up like that. Oh, I still have my other one. Hold on a second. Let's get my regular arrow back. There we go. Okay. So we're going to start at the center. We're going to go north, and then we're going to go to the west here, 30 degrees. Just like that. And let's move it over a little bit. There we go. Looks good. Okay, so if I want to put in my values here, I said this is 30 degrees, so that means this has got to be 60, right? Because they have to add up to 90. So I have that angle in between the x-axis and my vector. And this is the velocity, right? So I'll say velocity in the x direction is the velocity times the cosine of the angle. So that's 25 times the cosine of 60. Now, here's one catch. This is going, you'll notice in the, it's going west, right? My x component. And I've defined that as a negative direction. So I actually have to put a negative sign in here just to show that that's going to be going in the negative direction. So that's something you just need to kind of pay attention to. Are we going left? Are we going west? Are we going in the negative x direction? That's going to be a negative value because I've defined that as my negative direction. I'm not going to work out all of these because I kind of want to be snappy and go quick here, but you can do that if you like. Vy is going to be V sine theta. So we say that's, and this one's positive, right? It's going up. We say 25 sine 60 degrees. And if I want to actually draw what those look like, again, I can put my vectors on here. Let's draw my component vectors. Get out of there, you. Here's my x component. We notice it's going in our negative direction. My y component, we notice it's going in our positive direction. Okay, last one here. Let's draw this one on. We're going to say here is our vector. It's 10 meters per second squared south. So I'll start here and I'll go down like this, and it's directly south. You can see my calibration problems there. My tablet's a little off. There we are, directly south. Okay, so we'll say, okay, let's do our components here, right? And this is 10 meters per second squared, and it's directly south. So we say, okay, our x component is going to be the acceleration times the cosine of theta. What's the angle in between this vector and the x-axis? Well, it's 90 degrees, right? So acceleration is 10 cos of 90 degrees, end up with a value of 0. Sorry, this should have said ax, not bx. Ax, because it's acceleration. And my ay, my acceleration in the y direction, I could calculate it and put the angle of sine of 90 in there, but I can look at it. It's only 10. It's going directly south. It's actually, though, negative 10 because it's going down. So I'll have to put my negative value in there. Okay, time for you to try some of these out, okay? So on the lesson sheet, there's these examples. I'd like you to try these out. At the bottom of the sheet, at the back, there are answers, okay? And we'll see for example, let me get my highlighter here. For displacement, you can see there's dx and dy. For force, there's fx and fy. For acceleration for E, there's acceleration x and acceleration y. Okay, so what I'd like you to do is try these out now. Pause the video, give these a shot, give yourself some reps. Okay, if you finished all that and you're back, let's try tackling the two problems from the previous lessons. We had this chickadee flying, and we're going to try and tackle these using vector components. Okay, you may say, Mr. Roy, I prefer to use sine law and cosine law, and I'd say you can do that here, but it only works when you're adding two vectors. The second there's a third vector added, doesn't work anymore. Sine law, cosine law, out the window. So we're going to choose a better way to do this. We're going to choose a more robust tool to help us figure this out. Okay, and this is practice. So we're doing one we've already done, so that we can kind of be used to it and be like, oh yeah, we've already done this. So I feel good about it because I've already seen this one. I've already tried these ones. Okay, and if you can look back in the previous lesson if you want to check those out. So first of all, we have our first vector. It goes from P to B, right? There is an x component to that vector. It looks like this. And then there's a y component that looks like this. My next vector that goes from B to F, it has an x component that looks like this and a y component that looks like this. You'll notice the y component goes down. Now, if I were to add all these together, I'd have this x component and this x component, and I'd have this y component and this y component. And so what that works out to is like this, okay? And we can see that matches that. It's the same thing. So using vector components, I've turned this into a nice right angle triangle, like that. And right angle triangles are much easier to work with, right? We can just use basic trigonometry for those. So that's great. By just adding the two x components, two y components, I've got a nice right angle triangle. Sometimes you will have something that goes up and then comes back down. You want to say, where did I start? Where did I end? That's where I'm going to go. Okay, so I'm just going to get rid of that. what I'd like to do now is I'm going to do my vector component. So I see my first vector is a displacement vector, right? So I'll say, okay, I have a displacement vector, and I'm going to call this delta D1 because it's my first displacement vector, and the vector is 22 meters, and the direction of that vector is north 57 degrees east, or you could describe that as east 33 degrees north. And that's how I want to describe it because I want that angle next to the x-axis. There we go. So that's my vector. Let's do my x and my y components. For the x component of the vector, I'm going to take the total value of the vector, which is 22, and I'm going to multiply that by the cosine of the angle in between the x-axis. That's 33. Okay. Let's work that out. That works out to be 18.45075. So I just did the math on my calculator there. For the y component, we're going to say take the value of the vector, multiply it by the sine of the angle in between the vector and the x-axis. That was sine of 33 degrees. So what does that work out to? That works out to 11.982059. Got lots of decimal places there. Let's just do a quick sign check. Should both of these be positive? And the answer is yes, they should. This one is going in the positive x direction. This one is going in the positive y direction. So both of those should be positive. Okay, let's try the components for our other one. That vector is going to be another displacement vector, right? I'm adding displacement vectors here, so I'll call it delta D2. It's got a magnitude of 11 meters. And what's the direction? We could say east 28 degrees south. Now we want that angle in between the x-axis direction and the vector. So that 28 degrees is exactly what we want. That's good. So what are my x components? Again, I'll take the magnitude of the vector. It's 11. Multiply it by the cosine of 28. That works out to 9.71242. Okay, nice. Now I got my next one. Here's a catch. This one is going to end up being negative, right? I can see my x component's going in the positive x direction. My y component is going down. So my y component is actually going to be a negative value. So I'm going to put in a negative value there. I'm going to say negative 11 sine 28 degrees. That works out to negative 5.16419. Okay, now I did this with just two vectors. If there was a third vector, you put it in the third row. If there's a fourth vector, you'd add a fourth row and put it in there. Fifth vector, put it in the fifth row, right? We could do this on computers with spreadsheets, but I just want to show you by hand how we'll do it the first time. Okay, let's add our numbers together here. So I've got this 18.45. Like we're going to add all of our, let me get my color here. We're going to add our x component and our x component. And we're going to add our y component and our y component. And we're going to add all those together, okay? So we'll see what's our total x and what's our total y. And really what we're doing when we're adding those is you see these red dotted arrows, that's exactly what we're doing. And so we're just finding the value of those and we're adding them together to see how far we go. Okay, let's add our first ones together. The sum of 18.45075 and 9.71292, just add those together. We're going to end up with 28.16317. And for adding our y's together, we've got positive 11.98 and change, and then we've got negative 5.16 and change. So we add those together, and we're going to end up with 6.81787. So This one's 28, 6317, like that. And this one is 6.81787. I should be clear. The 6.8, blah, 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 we're only talking about this part here. We went up and then back down. So we're only talking about that first part. If I'm to highlight it here, we're only talking about this part here. That's our x component, or y component rather, and this part's our x component. Okay, so now we're almost there. We got just a little more to do. And we're going to get really fast at this, so you're going to get used to this. So we've got our triangle, right? And I think I'd like to redraw the triangle just to make it a little easier to work with. So let's scroll down a little bit and we'll redraw our triangle here. We say, okay, I've got this first one that's 28. It's in the x direction. It's going like that. And then I got my second one that's 6.8. It's in the y direction. It's going like that. I got my resultant vector. It's going to go like this, and I want to figure out that resultant vector. What's the magnitude and what's the direction? So let's do that. We're going to need the direction, and we're going to need the magnitude. And we note this is a displacement vector, so we'll say the displacement, and I'll put a little r here for resultant. Right? That just means we're adding the vectors together. And this is a right angle triangle. That's why we did it. Gives us a nice right angle triangle, easy to work with. Okay, let's do a little math on that. I'm going to say my displacement vector, if I want to figure that out, I got to use Pythagorean theorem. So to use Pythagorean theorem, we're going to get the square roots of both sides. We're going to say 28.16317 squared plus 6.81787 squared. I'm doing this kind of messy and quick, but this is just Pythagorean theorem, right? We're pretty good with this. So we say, okay, the magnitude is going to end up being 28.97667. Okay, that's our magnitude. What's our angle? We're going to use our tan ratio again for this. So say inverse tan. Tan is opposite over adjacent. The opposite side is the 6.8. The adjacent side is the 28. You might say, Mr. Wright, you're using a lot of decimal places. Why are you carrying all these decimal places? I just like to be precise, and I hope you do too. Okay, it looks like our angle is going to be 13.60861. Now that's the angle in regards to east, right? So now let's write our final thing. We'll say, okay, our displacement vector, the resultant is going to be the following. We're going to round off to 2 significant digits here because that's what's in my problem. So I'm going to say the displacement rounds off to 29 meters, and my direction is going to be east, 14 degrees towards the north. I'll put a box around it to show that's my final answer. And lo and behold, this is the same answer we got last time when we used the sine law and the cosine law. But now we're using our new, more powerful method. Okay, I'm going to flip to my last one here. If you're feeling okay about this, I'd like you to just try it on your own and see how it goes. If you're still feeling a little shaky, you can just watch me as I work through this. Okay, so decide how to do it based on where you're at in your given skill level. Here's a question we already did. We already did this in the previous lesson. Two-dimensional non-right angle vectors, but we're going to use the component method this time. We got. And I decided I was going to make this, rather than have no units, I'm going to give this velocity units this time. So we can talk about it as if it's velocity. 46 meters per second, north 80 degrees west, and then 117 meters per second, south 40 degrees west. Let's get those little grids here. I want to grab a couple of those and take them with me because I like them a lot, and they're going to make our lives a little bit easier. Here we go. Okay, let's actually draw what this looks like. Okay, I think I'll draw it over here, actually. Our first vector is 46 meters per second north, 80 degrees west. So let's draw what that looks like. I'm going to go north. Oh, no, I don't want you to be red. I want you to be solid and black color. Okay, good. So I'm going to go north, just like that. And then I'm going to go 80 degrees to the west. So that's not the whole way, but it's close, right? I'll get right to there. Okay, that's my first one. Now let's draw our second one on here. I'm going to put this right here so I know exactly where to draw it. That'll just help me a little bit with clarity there. Okay, my next one was going to go 117 meters per second south, 40 degrees west. So let's start by going straight south, and then we'll head 40 degrees, which is not quite halfway. Half would be 45, so it's like there, something like that, right? Okay, and our resultant vector is going to start at the beginning and end at the end. It's going to look like that. Nice. Okay. So I'm going to need to do this. Last time I had to put in all these angles and figure out all this stuff, and it was a real pain. This time is going to be easier with vector components. Now I need to know the angles next to the x-axis. So I remembered that this one was 80, so this one's got to be 10 degrees in here. And this next one over here, I know that I was south 40 degrees to the west, so this has got to be 50 in here. So now I have the angles next to my x-axis, and the ones that I wanted were the 50 and the 10, because those are next to the x-axis. So those are the ones I'm going to use. Okay, let's go to our table here. Our first vector we said was, and these are a velocity vector, right? So I'll say my first velocity vector is going to be 46 meters per second, and my direction is, I could say, west 10 degrees to the north. I could also have written that as north 80 degrees west, but works out the same. Okay, now I notice, first of all, this one is going, my x component is going to be negative because it's headed left, right? So I got to put a negative value in here. And I'll say negative 46 cosine 10 degrees. What's that work out to? That's going to be negative 45.30116. Okay, there we go. What's my y component? My y component, it's going up, so my y component is going to be positive here. So I'll say, okay, it's 46 sine 10 degrees. 10 degrees. What's that work out to? Sine 46 degrees. It's 7.98782. Okay, my next vector. Second velocity vector, 117 meters per second. And we see that we're going west 50 degrees towards the south. Okay, this vector I notice is going left and down. So that means both of these are going to be negative. The x component is going to be negative, the y component is going to be negative. So we'll say, all right, it's going to be negative 117 cosine 50 degrees. And then we've got, that's going to work out to negative 75.20615. My y component is going to be negative as well. So it's going to be negative 117 sine 50 degrees. That works out to be negative 89.62720. Okay, let's add them up. Let's do a little bit of adding here. Let's add up our x components and see what we get. Let's add up our y components and see what we get. Adding up all our x components, I got two negative numbers, so I'm going to end up with a big negative number. It's negative 120 and change. My y components, I've got a small positive number, 8, around 8, and then a big negative number around negative 90. That's going to work out to negative 81 and change. Okay, My next step is I got to draw these two, right? I've got my two vector components. I added up all the x's. I added up all the y's. Let's draw them. First of all, added up all the x's. It's negative 120, which means I'm going this direction, like this. And then I added up all the y's, and it's negative 81. So it's going to be down, like this. My resultant vector is going to start at the beginning. It's going to end at the end. It's going to look like this. And if we actually look at the one up here, oh, look, they match. But up here, I didn't know what it was. Now down here, I can figure it out easy with this nice right angle triangle. Ah, brilliant. That's what we want. That's what we want to make it easy. Let's put a theta in there. Let's put our values in here. And this one's going to be... Okay, now I'm going to do what I did before. How do I figure out the resultant velocity? What's it going to be? Well, I got to use Pythagorean theorem, and then I got to use tan ratio. Let's do those. But let's do them nice and quick because we're like pretty good at this now. Pythagorean theorem. My resultant velocity. It's going to be the square root of these two numbers. 120.50731 squared plus 81.63938. Now you might say, Mr. Roy, why aren't you using negative numbers there? I'm just trying to find the magnitude. I'm just trying to find how big it is. And if you square a negative number, you get a positive number anyway, so it wouldn't make a difference. That works out to 145.55755. Let's do the angle. It's going to be a tan ratio because it's opposite and adjacent. My opposite side to my angle is my 81. Hey, Mr. Roy, why didn't you put this in as a negative number? Well, it's a negative number on the top and bottom. They're going to cancel each other out. Nice. Let's see what we get for our angle. Works out to 34.11623. Okay, let's do our final answer here, our resultant velocity. Let's round this off to one significant digit because that's what the angles that we had were rounded off to. So one significant digit, 145. It's going to round off a lot. That's going to round off to 100 meters per second. And our angle is going to be 30 degrees. So it's going to be west 30 degrees towards the south. There we go. Let's put a box around it. Okay. So that's all our example problems. These are a little long. They do take a bit of work. Let's just do a really quick recap of what we're doing. We look at our vectors that we're adding up, no matter how many there are. We draw a picture of what they look like. Just sketch it out quick. We draw a cute little table. In each of the table, we take each of the vectors and we take their x and y components. We add up all the x components of all the vectors. We add up all the y components of all the vectors. We draw all the x components added up together and all the y components added up together, and that makes this nice little right angle triangle, which we love to work with. Then we draw our resultant vector. We use Pythagorean theorem to figure out the magnitude, tan ratio to figure out the angle. This would be just as easy if we had 5, 10, 20, or 100 vectors. Now, maybe not as easy. It would be more work. But the complexity of the problem and what you're doing doesn't actually get any harder. Whereas if you try and use sine law, cos law, all those things, every new vector you add, it gets insanely harder. So this technique is going to work for any number of vectors. It's going to be a very powerful one. Okay, now's a chance to go do some practice and try this out. I want to wish you good luck. Practice hard and let me know how it goes for you. Bye for now.